In this video, I will introduce you how to use the slope and gnuplot to study some problem about ordinary differential equations. We consider this example. We will find the solution of this initial value problem, and also we will plot the graph of the solution, and also determine the interval where the solution is defined. The equation is separable, therefore we can rewrite this in this form, in blue. Then integrating both sides of this equality, we find that the general solution is given by this formula. Then we apply the initial value condition to determine the constant c here, and it is easy to see that c is -3. Okay. Therefore, the solution is this one, implicitly given by this equality. This is a quadratic equation on y, so we can solve for y using the famous formula to see that y will have two roots corresponding to positive and negative. Taking the initial value condition into account, we need to take the positive side. Therefore, our final answer about the solution of the initial value problem is given by this blue formula. Okay, so we'll plot the graph of this formula using slope. I introduced you to you previously. So this is the web page, and we input the equation. The equation I already prepared here. Okay, we place the expression y prime equal 3x squared minus ex over 2y minus 5. This is exactly our equation. So we press enter, and we get the direction field of the equation. And of course, as before, to get final result, we increase the number of the segments in both x and y direction. And this is a much better picture of the direction field. And to plot the solution, we need to take the initial value condition y0 equal to 1. Okay, y0 equal to 1, so we enter 0, 1 here, x equal to 0, y equal to 1, and submit. So we get this red curve. This should be the graph of our solution. But the left half of this picture of this curve seems crazy. Okay, this is because the h here is too large. 0.1 is too large. We decrease this to get a final result. So maybe 0.01 switch. So the curve becomes smooth and looks more reasonable. But this is only half of the curve. We don't know what happened on the upper half of the curve. Therefore, we need to change the range of the variable. So our y may be 5. We can try 5. Okay, so we enlarge the range of y and see that the curve look like this. This seems very good. Okay, of course we can also have other integral curve of the solution. So this is several of them, but the red one is the graph of our initial value problem. Of course, you should know that the red curve is also not a graph of a function. Because as a graph of function, the line parallel to the y-axis can have at most one intersection with the curve. But here we have two. Okay, so this red curve is in fact the union of the graph of two functions. To our initial value problem, because 0, 1, this point should be lies on the solution on the graph. Therefore, only the lower half of this red curve is the graph of our solution. Okay, the upper half of the curve is the graph of the same equation, which different initial condition. Okay, so this is the graph of the solution of our initial value problem. So so we need to determine the existing interval. That is the interval where the solution is defined. So from the expression of this equation, we see that make this for this to make sense, we need to assure that the expression inside the square root sign to be non-negative. So the range of x, so that this makes sense, is determined by this inequality. This inequality, x cubed, and here is an exponential function. So this inequality could not be solved analytically. Therefore, we can only try to find the numerical solution. So to solve this equation numerically, we study the graph of this function. This function is the left-hand side of our inequality. So to study the graph, we will use this very useful software, gnuplot, to plot the graph of this function f, and from the graph we can figure out the x, so that this equation, the solution of our initial value problem is defined. Okay, so we consider this. We run this gnuplot software, and we need to set something. Firstly, we set the line type. I set a line type red and white and something we don't care. And then we need to set the range of the variables. For example, the y variable we can maybe, firstly I will try maybe -3. Okay, and similarly the x, the range of x, then we can plot our equation, our function. Our function is 4x squared minus 4 exponential x plus 13. So this expression should be typed in this way. Okay, then we press enter, we will get the graph of the function. So this is the graph. From this graph, because 0 is here, so the intersection of this graph, which the lower boundary of this rectangle, is not a root. Okay, this is why we need to set y range to be 0, start from 0, not -3 or anything else. You have to start with 0. We set y range to be 0, start with 0, and then we plot the curve. Then this is the curve. Now the lower boundary of this rectangle is the x-axis, that is y equal to 0. Therefore, the intersection of this curve, which the lower boundary, the x coordinate is one root of f equal to 0. Okay, so the first one is -1 point. You can read the coordinate of this point from the lower left corner of this window. Okay, this window displaying the graph. So here we see that the x coordinate of the intersection of the red curve, which the lower boundary, which is the x-axis, is 1.446. Okay, something. And the other intersection, the coordinate of the other intersection is 4.63970. So these two, the x coordinate of these two intersections determine an interval. In this interval, f is positive, f is non-negative. Therefore, this interval is the interval where our solution is defined. So, so this is the answer of our question. The interval where the solution of the initial value problem is defined. Now we observe that the existing interval is bounded on both sides. It has a left endpoint and a right endpoint. Therefore, it's interesting to study the behavior of the solution when x approaches to these two endpoints. So let's go back to the graph of this integral curve we plotted previously. So we see that this curve, some part of this curve is outside the scope of this picture. Therefore, we should change the range of x and y. Here we change x to be maybe -2 to maybe here is 5, because the interval -1.4 and 6.6. Therefore, we should let x valid in an interval containing this interval. Therefore, we choose -2 and 5. And here is the new plot. But we see that part of this integral curve is still out of the scope of this picture. So we increase the range of y more a little bit, maybe 7. We try, and we see that the curve becomes like this. Therefore, we see that this is the integral curve of our differential equation passing this point 0, 1, determined by the initial value condition. And this integral curve has vertical tangent at the two endpoints of this existing interval, x equal to -1.4 and 4.6. So when x equal to -1.4 and 4.6, this curve has vertical tangent. And in fact, this curve consists of two graphs of solutions. The lower half of this curve is the graph of solution of our initial value problem. The upper half of this curve is the graph of the solutions of another initial value problem. The same equation which in different initial value condition determined by maybe, for example, this point, the intersection of this curve which the y-axis here. Okay, so this picture will be more complete than the previous one. Okay.